Welcome to the Deep Dive. We cut through the noise on complex topics, giving you the insights you need, faster. Today, we're jumping into something pretty fascinating in the world of electronics. Tunable microwave filters. Specifically, a really new class, these resonator-loaded waveguide notch filters. Now, this might sound technical, but it's really about making our communication systems, the backbone of everything, much more flexible and efficient. That's key for the huge growth we're seeing in telecoms.
Exactly. We're digging into an academic paper here. It's from the journal Electronics by Hawk, Koziel, and Petrenko-Dabrowska. Our mission really is to unpack their innovative approach, understand why it's a big deal, and see how it could genuinely change things for high-frequency communication. We want to give you those aha moments without burying you in jargon.
Okay, let's set the stage then. What's the fundamental problem they're trying to crack here? Because these notch filters, even if you haven't heard of them, they're actually really key bits of kit in RF communication systems, right? And the demand now is just huge for systems that handle multiple channels, multiple standards. They need to be high performance, tiny, lightweight, and critically tunable over a wide frequency range. So what are the roadblocks? What makes that so hard?
Well, yeah, it's a tough set of requirements.
Hmm.
Previous attempts, looking at both flat planar filters and the 3D types, they've really hit some walls. Often they just couldn't handle the power levels needed. Or they weren't good enough at blocking unwanted signals, especially at higher frequencies. Plus, integration could be really complex, just not suitable for the high-performance stuff. Even the methods using, say, electrical or magnetic tuning, or even mechanical adjustments, things like substrate integrated waveguides or special cavities, they tend to have a pretty limited tuning range. We're talking maybe just a few percent, sometimes up to about maybe 19.4% in some cases. That's often just not enough flexibility.
Right, so a real bottleneck. High performance needed, but tuning is limited and complex. So let's get into this new solution. What exactly did these researchers cook up?
Okay, so they've come up with a novel design. It's a resonator-loaded waveguide notch filter, specifically targeting high-frequency use. At its heart, it uses a standard rectangular waveguide, specifically a WR-28 type. Now, waveguides like this are common in high-frequency work, say between 20 and 40 gigahertz. They're great because they have very low signal loss and can handle significant power. Think of it like a precisely shaped metal pipe for guiding microwaves. This one's about 7.1 by 3.6 millimeters. Inside this waveguide, they excite a microstrip transmission line, or MTL, that's essentially a precisely patterned conductive strip on a special circuit board material, an RO4303C substrate in this case. And crucially, this MTL is connected to something called a complementary asymmetric split-ring resonator, the CAS-SRR. You can picture the CAS-SRR as like a tiny complex metal shape etched into the board's ground layer. It's designed to resonate strongly with magnetic fields at specific frequencies. It's got 5 key dimensions defining its exact shape.
Okay, that's quite a setup. Waveguide, microstrip line, this special resonator. How does putting all that together actually create the notch? Why does that combination work to filter out a specific frequency?
Right, so the core principle is interference. It's a bit like noise-canceling headphones, but for electromagnetic waves. By putting this resonant structure, the CAS-SRR and the MTL, inside the waveguide, you set up conditions for destructive interference, but only at a very specific frequency. See, at its resonant frequency, that CASRR generates these strong circulating surface currents, electrons whizzing around. This creates a powerful localized magnetic response. Now, when an electromagnetic wave traveling down the waveguide hits this spot, if it's at the resonant frequency, that magnetic response interacts with it and basically cancels it out or strongly attenuates it. Other frequencies, they pass right through, mostly unaffected. So you get this sharp notch in the frequency response. It's frequency selective.
Okay, that makes sense. Destructive interference powered by that resonator's magnetic field. So how did it perform? What were the actual results when they built and tested this?
They optimized it for the Ka band, which is roughly 26.5 up to 40 gigahertz, a really important band for modern communications. Their simulations predicted resonance around 32.88 gigahertz, with a really deep notch minus 29 decibels, which is strong rejection, and a bandwidth of about 2.4 gigahertz. Then they actually built it, using standard photolithography. The experimental results showed resonance at 31.43 gigahertz. The measured notch wasn't quite as deep, negative 13.5 gigahertz, and the bandwidth was wider, about 4.8 gigahertz.
So a bit of a difference between simulation and the real thing, about 1.5 gigahertz shift.
Yeah, about 1.58 gigahertz different in the center frequency. That's actually pretty typical, though. They put it down to normal fabrication tolerances, tiny variations in dimensions, maybe the material properties weren't exactly as modeled, or slight misalignments during assembly, it happens. But the key thing is the principle worked. And importantly, it pointed towards significant advantages, potentially a wide tuning range and lower manufacturing costs compared to some other common structures like SIW or MMICs.
Okay, impressive initial results, even with that slight discrepancy. But the really big deal you mentioned was the tuning. How did they achieve that? Because you said the old ways were clunky.
This is where it gets really clever, I think. Yes, traditional tuning often meant physically moving things around, like changing the resonator's height inside the waveguide or rotating it. They showed that could work. Changing height shifted the frequency from about 33 gigahertz down to 25 gigahertz. Rotating it gave a smaller shift. But these methods need extra mechanical parts, slides, discs, motors sometimes. It adds complexity and bulk, and the range is often still limited. Their breakthrough is using additive manufacturing, but in a really simple way, adding copper patches.
Copper patches, just as sticking bits of copper on.
Essentially, yes. It sounds almost too simple, but it's highly effective and reliable. Remember that microstrip transmission line, the MPL? Its exact geometric dimensions are critical for determining the filter's resonant frequency. So by carefully adding a small, thin copper patch onto the MTL, they effectively change its electrical length or capacitance in a very controlled way.
Wow, okay, so you're altering the circuit just by adding a tiny bit of metal. That is simple. How much tuning did they actually get with this patch method? Give us an example.
They did systematic tests. They used a very thin, square copper patch, just 0.1 millimeters thick, placed right in the center of the MPL. And get this, as they increased the size of that square patch, from 2 millimeters across up to 4 millimeters, the filter's resonant frequency dropped dramatically. It went from 32.16 gigahertz all the way down to 23.48 gigahertz.
Whoa, hold on. From over 32 down to under 23.5. That's what, nearly 9 gigahertz of tuning range? Just by changing the size of that little patch.
Exactly. A substantial tuning capability achieved with a very straightforward post-fabrication step.
That's incredible. But okay, practicality check. How do you know exactly what size patch you need if you want, say, exactly 25 gigahertz? Is it just guesswork, sticking on patches until it looks right?
No, they thought of that too. This is another neat part. They didn't want trial and error. They took all the measurement data they gathered from testing different patch sizes and used it to build an inverse regression model. It's basically a mathematical formula derived from the real-world data. This model lets you do the opposite calculation. You tell it the target frequency you want, say 27 gigahertz, and it tells you the precise patch size you need to achieve it.
A calibration curve, essentially.
Precisely, a predictive calibration model. They gave examples. A 2.05 millimeter patch gave them 31.02 gigahertz in reality. A 3.01 millimeter patch resulted in 26.77 gigahertz. A 3.99 millimeter one hit 23.68 gigahertz. They even provided the equation. D is 19.285, 0.9938 feet plus 0.012 gigahertz. Okay, so they've got a predictive model. Did they test that? Did the model's predictions hold up when they tried to hit specific frequencies? They did exactly that for validation. They picked 4 target frequencies spread across the range, 24, 26, 28, and 30 gigahertz. The model predicted the required patch sizes, 3.88 millimeters, 3.54 millimeters, 2.69 millimeters, and 2.24 millimeters, respectively. Then they made filters with those exact patch sizes and measured them. The results were remarkably close. For the 24 gigahertz target, they measured 23.07 gigahertz. For 26 gigahertz, they got 25.85 gigahertz. For 28, it was 28.25 gigahertz, and for 30, it was 30.07 gigahertz. Really good agreement.
Wow, that's very accurate. So the model really works.
Yes, it demonstrates the robustness of the approach. They even estimated that for practical manufacturing, to hit a target within a tight 0.2 gigahertz window with 90% certainty, you'd probably only need between 3 and 6 attempts at placing the patch, which for a physical tuning process is actually pretty efficient.
So let's bring this back to the bigger picture for you listening. What does this mean in the real world? Where could these highly tunable, cheaper filters actually be used? Why is this Ki-band tuning so important?
Well, that Ka-band frequency range, 26.5 to 40 gigahertz, it's incredibly important. It's used for loads of current and emerging applications. Think about high-capacity wireless personal area networks connecting devices in a small area really fast. That often uses frequencies around 28 to 32 gigahertz. Crucially, 5G radio systems rely heavily on these higher frequency bands, especially for things like outdoor microcells around 32 gigahertz, to get that massive bandwidth and low latency. It's also being explored for things like ultra-reliable low-latency communications needed for industrial automation or remote surgery using bands between 26 and 32 gigahertz, and even slightly more niche things like using millimeter waves for non-invasive diagnosis of skin burns.
Okay, so a wide range of really demanding applications.
Exactly. And these filters can slot into either the transmitter or the receiver side of these systems, precisely knocking out potentially interfering signals at specific frequencies, which can now be easily adjusted. The key competitive edge here is that broad 8 gigahertz tuning range they demonstrated from about 23.7 gigahertz to 31 gigahertz. That represents nearly 27% tuning relative to the center frequency. That's significantly better than many other state-of-the-art tuning methods, which often top out between, say, 4% and maybe 23.5%.
Right, a bigger tuning window means more flexibility.
Precisely. And achieved with an approach that is simple, low-cost, generic. You could potentially apply this patch tuning idea to other types of resonator-loaded filters too. And importantly, it allows post-fabrication tuning. You make the basic filter, then tune it precisely afterwards.
It really does feel like a significant step up in practicality and performance. Where do they go from here? What's the next step for this research?
Well, like any research, there are areas for improvement. They mentioned that getting really precise control over both the center frequency and the bandwidth simultaneously was initially tricky due to the complex geometry, although they tackled that with optimization. Looking forward, the focus will likely be on further optimizing the design. A key goal will be minimizing what's called insertion loss.
That's the signal you lose just by having the filter in the path, right?
Exactly. Currently, after adding the patch, the loss was between 2.0 and 2.88 dBo. They'll want to get that lower, and generally just boost the overall efficiency. But the core concept looks incredibly promising.
This whole deep dive really highlights something interesting, doesn't it? How sometimes combining established tech like waveguides with clever, almost simple-seeming innovations like additive patches can unlock solutions to problems that have been around for ages in complex fields like telecommunications.
It really does. It's a great example of that. The ability to fine-tune something so critical, so precisely, using just a tiny bit of copper after it's been made. It changes the game for manufacturing and designing these high-frequency systems, makes them potentially much more adaptable, much more efficient. It definitely makes you pause and think, what other really complex engineering hurdles out there might just be waiting for a similarly elegant, perhaps unexpectedly simple, solution using materials we already have readily available.